we're going to have scheduled for the 18th.
Recording is on.
7:30 at night.
Wow.
So at least,
Well, at least they're going after hours.
The drugstores down here don't have any. And don't around here, around west end of Mississauga, don't seem to have any available till much later.
So let's put that on the agenda for when Eric signs in. Eric, buddy, can you help me out?
So we get Eric, fun to get Eric to show up, and now Kevin's gone. Oh, dear.
Yeah, but he won't be gone for long.
No, as soon as Kevin's back, we'll get started.
Okay, I'm here.
There you go.
There he is.
Okay, so let's get started then. Well, welcome everybody to the December meeting, the regular meeting of the month, and don't see anybody new. And let's see. Oh, there's the new. I posted up the new Jitsi schedule up at the Homebrew section of the club website. So if you want to take a look at who's doing what when, that's there. And I guess that's pretty much all I have for the opening remark kind of thing. So tonight we have two presentations. Kevin with Citizen Radio Science. It's not CB. And myself, I'll do an LT Spice in the Real World, the third of a series, the instrument amplifier, not a Fender. And then, of course, we'll have time if anybody else would like to talk about something else or bring up something, and we'll have lots of time for that. Okay, so I guess, Kevin, if you want to...
Okay, let me get the right window here. There, that should... Okay. Everybody see the PowerPoint there?
Mm-hmm.
Yeah.
Okay, so anyway, this is nothing too fancy, but it's just, I fell down this rabbit hole and I thought, oh, this is kind of interesting. So I wanted to see what else was all out there. And this is not so much a deep dive into the science, but just some stuff that I found digging around on the web. I mean, it started with the Hamsai Group that was at Dayton a couple of years ago. And, what's his name? Nathaniel, somebody, I forget his last. But he does all this analysis with the big data sets from Whisper and the reverse beacon network and that kind of stuff. And anyway, I started digging around, and this is sort of the results of what I found. Some people may find it interesting. It's something I would like to get into, and actually the Hamsai Group is something neat going to be coming out soon. So anyway, with that said, there we go. So I'm going to start with this one, which is SatNogs. I don't know what that even stands for, but it's part of the Libra Space Foundation. And so their goal is to do all this open source development on, as I said, space technologies, right up to rockets and everything else. But this specific part of this is they've got an open source design and software interface to build your own ground station. And really all it's supposed to do is track satellites, and any satellite you want, apparently you can. And then what it does is feeds the data back into a cloud database that anybody can go look at. Excuse me, the websites are on there. There's a whole bunch of stuff that you can go looking at. This was a map of some of the locations and current satellite stations around Europe. There's a bunch around North America, not nearly as many, as you can see. But they have, like I said, it's got everything you need, apparently, to do your own satellite ground station. And they've got, they've even got plans for a rotator, a lot of 3D printed parts, I think, and all the instructions and the build, the bill of material and that sort of thing is on there. And you can see they've got 260 operational stations, 120 in testing, and they're observing over 700 satellites. And not sure what's going to happen when Elon Musk and Bezos get all their Starlink and whatever else satellites up there. That might be a bit overwhelming. I don't know. But and I just had. I'm going to switch. Excuse me. I'm going to switch windows here. If I find the right one. Yeah. So this is from the SatNog's website database, and it's just tells you what satellite it was, what frequency, when it was observed, the path across the sky. It gives you this guy, I guess, has an SDR. It looks like he has a waterfall and then they've got audio and data and telemetry recordings. If I'm not particularly into that, but I'm sure it could be useful, and I'm not sure what you could use it for, but I just thought it was interesting that there's all these people collecting all this data and putting it out there for everybody. Anyway, and it's got a brief description of all the satellites and such that it monitors, and these things are just continually pouring in, right, in real time from all over the place. So that's one. Hang on, I'm gonna go back to my presentation now. If I can find it here. What I do with, oh, there it is. Sorry, a bit of flipping around here because I was too lazy to take all this stuff and put it on slides. So I'm just gonna go back and forth between this and a couple of PDFs, and so that's one. And then I think the most interesting one is the Hamsai Group, started by a bunch of ham radio operators / scientists, I guess, who study the ionosphere and space physics and stuff like that. And as I said, they've been doing work with the RBN, Whisper, PSK Reporter, and even during the last eclipse, I know they ran some. They were encouraging everybody to get on Whisper and all this kind of stuff, and RBN, so that they could collect data on how the eclipse affected transmission and how it affected the ionosphere. And as you can see, some of their goals are, they want to study solar flares, ionospheric storms, traveling, like what they call them, traveling wave disturbances or something like that. There's all these phenomena that I had no idea exists, but they're studying this using ham radio stuff and some various sensors. So one of the things they've got now, and they've got a few deployed, and I guess it's like a precursor to what they really want to do. And they've got they call it a grape receiver, and basically it's like the DC receiver. It's basically a software-defined radio with some bandpass filters out in front of it, and it brings the signal down to baseband, and all they're listening for is the time stations. So WWV in the US and CHU up here in Canada. And they have that with an oscillator, and then a Raspberry Pi does a bunch of data analysis on the signal as it comes in through a sound card. And I think that they're looking like down at the level of 1 millihertz, so 0.001 hertz.
Good.
So thus the GPS disciplined oscillator. I know this thing works in some of the ICOM radios. I think that's why he developed it, for frequency stability. But they're using it as a third-party oscillator, or as a local oscillator for their receiver. So anyway, that's that's what they're doing now, and what they want to do is some of this other stuff. Like there's that solar eclipse in Antarctica when it was a couple of weeks ago, I think. So anyway, they were studying some stuff there. They've got, apparently there's some radio transmitters they use as basically big radar units. They send signals up into the ionosphere and try and measure what's going on with it. And I think they're called Super Darn or something like that. And they do that. So I'm just what they want to do is going to be, let me find the PDF here. Let's do this. So what they want to do is like a generation 2 thing. And this is, I believe it's in progress right now. I know they're testing some stuff. They had a presentation on QSO today about this as well. When that was last on, back in, when was it, September? So they want to use some of these various instruments. So, you know, the big data stuff, Whisper and PSK Reporter. They monitor WWV. They're working on a ground magnetometer, something down on the order of like 10 nanoteslas for sensitivity. They actually have to bury it in the ground because they think that the testing they were doing was so sensitive. If you walked by with a wheelbarrow, it would detect it. So they're doing some stuff like that. They have a GPS total electron receiver or total electron count receiver, so they can use that to detect changes in the GPS signals, lightning detector, a rheometer, which I forget what that is, but we'll know in a minute here. So, oops. Hang on, let me go one page at a time. So there. So PSK Reporter, and this shows some of the differences between solar flares and not, and they're using, you know, the WhisperNet and such like that to calculate all that. This ground magnetometer, so they want to be able to detect, you know, geomagnetic storms and substorms with that. The GPS total electron count, so there you go. So it measures it by examining the delay between two different GPS frequencies. And again, the traveling ionospheric disturbances, storm effects. It's like they seem to be able to pull an awful lot of data about some of this stuff with relatively simple measurements. And then this rheometer, relative ionospheric opacity meter. So there you go. So it measures the absorption of cosmic rays. And the lightning detector, just to add something to it. So they want to put all this stuff into an SDR with the GPS, your magnetometer, probably through, you know, like a Raspberry Pi or something again, and then feed it up to the internet. And then they're going to have like a public database of all these observations all around, hopefully the world, I guess. And I thought that was, that one looks really interesting. I think this whole kit that they're talking about, they're aiming for like $500 or something to make it available for anybody that wants one. And this is some of the hardware that I guess they've been looking at. For the SDR, it was the Red Pitaya, some antenna array. That's that GPS disciplined oscillator, and some magnetometer from the British survey. Anyway, that's that one. I think that's probably one of the most interesting ones, just because of the amount of data they're going to collect. Is going to be interesting to see what they can get out of it. Okay, what else do I want here? I want to go back to presentation. Okay, so another one I found was this Radio Jove project. It's sponsored by NASA, and what they're doing is listening around, I think it's 18 to 22 megahertz, and they're listening for radio emissions from mainly Jupiter, but also the sun, the galaxy, that sort of thing. And I guess there's all these radio emission modes that Jupiter does, which I had no idea Jupiter was a radio emitter, but apparently so. And it's the same kind of thing. They've got a little receiver designed for the frequency that they're interested in. You can use a ham receiver if you can turn the AGC off, as they say. And then they've got a suggested antenna set up here, a phased dipole array. And then you feed that again into, a computer through an analog card, and they give you some software, and then you can, again, send it up to the cloud, and you get all this data that people collect. And I'm not sure what it all means, but this is the kind of stuff that they're pulling out of the sky with these quite simple receivers. I think this one's only like $50 or something like that as a kit. And then there's another one. This one is from Stanford, Sudden Ionospheric Disturbance Monitor. And so what they're doing, this one's more geared towards schools and like high schools and students and that sort of thing. It's relatively cheap and easy to build, or a cheap kit, and it's an easy to build loop antenna. And they're not as ambitious in their data collection, but they still want to, they can detect solar flares and ionospheric activities and things like that. But they're doing it by monitoring the VLF range. So what they, and this is sort of typical of what they've got. They've got this little receiver, literally, go back here. So they've got a little receiver here, and that's just powered by a wall wart, and that goes into your sound card. They've got, these are different loop antennas that the kids have made. And all they do is they listen for all these VLF transmitters, mainly the U.S. Navy submarine transmitters, because they're transmitting at whatever it is, 20 kilohertz, 30 kilohertz around the world. Oops, wrong way. And they've got them now like 1,000 of these out there around the world. And these things are all feeding data back into this database. And I'm just going to say I've got when I get, no, not right. It's hard to see which window is which here. Oh, that's it.
It looked like there was one receiver in the entire U.S.
No, there's hundreds. They just have it there, but the list is like, I think there was like 400 or 500. And this is, and I don't even know what all this is, but this is some of the data from, was it today? Yeah, no, December 10th. Okay, so a few days ago. And these are various stations recording emissions, and so it's looking for reflections from the ionosphere, right? And so as you go through the day, you're getting different levels of reflections around at different places in the world. Anyway, it's all logged and graphed, and I'm sure it means something to guys that are a lot smarter than me when it comes to this stuff. So, but it's just cool that you're collecting all this data for these guys, or for anybody that wants it, actually. And I don't know how useful it would be for us, like to help with predictions for ionospheric, conditions and propagation and stuff. But I'm sure there's something there that can be pulled out. Oh, there was one thing I forgot here. I was going to. One thing I wanted to show here. This was, sorry, to go, I'm just going to jump back to the Hamsai. This is one of the things that was in the QSO today presentation that this guy was talking about. And this is what the Hamsai guys are trying to do, is because they're listening to WWV, so you know the frequency. And so what they're trying to do is map the height of the ionosphere with just a receiver. And so they've developed this model where, if you have one hop, it's, you've got a certain layer height, it's a certain time of flight. 2 hops, it's a little bit longer. 3 hops, a little bit longer. But what they're doing and calculating is that if the ionosphere is moving down, the rate of change of the time of flight is one number. But if you've got 2 hops, well, then the rate of change increases, right? And if you've got 3 hops, the rate of change increases even more. And that's what this is showing it, is that they're calculating that depending on the number of hops and how fast the ionosphere is moving, you can, start back calculating what it's doing. and they actually took some readings here where they measured time of flights from, some, I forget what, that goes in more detail down here, between a couple of stations. And then they plotted on these graphs. And as you can see, there's pretty decent correlation. So they're using these simple receivers to calculate ionospheric heights without any transmitters, without your own transmitter. You're using, somebody else's. So anyway, I thought that was pretty cool that they were able to do that and correlate that. And now we'll go back to slideshow. Okay. All right. So anyway, sorry that this. So the Stanford one, yes, it's the same idea. Whoops. And then I also found that there's lists of these projects online. NASA maintains a list, and I mean, there's not all of these are radio. In fact, a lot of them are not radio. They're sort of biology related or natural science related, like data collection about, animals you see or plants or whatever. But so the Canadian government has a couple of websites, and also there's an American government website that lists all these projects. Some are, and it tells you whether they're active, recruiting people or not, and that sort of thing. So anyway, I thought that was kind of interesting that, even us non-scientific people can get involved and help out. So anyway, let me go back here and I'll turn this off. There we go. So anyway, that was my rabbit hole that I fell down one day.
Go ahead, Dave.
Yeah, Kevin, it's kind of very interesting. You're falling down the same rabbit hole I did when I met with those guys. The interesting thing is they've got a Groups IO forum that if you want to participate in, they talk about all their experiments, what's going on, a lot of ionospheric science going on. A lot of it you just won't understand. The other interesting thing is that red Pitaya platform.
Mm-hmm.
Okay, remember when I fell down that rabbit hole with the Ionosond?
Yeah.
Okay,
That was a good rabbit hole.
They made one with that. They had they used that, and I can't remember the guy I met with. I think Peter, you were with me when we sat through a presentation they gave about how it works.
Yeah, I'll get his name.
Yeah, and so he was using that platform to do a Ionosond. And so
Ward Silver, was it?
What's that?
Was it Ward Silver?
No. It wasn't Ward Silver. It was another guy. Because a lot of those Hamsai guys, they're PhD candidates. They're all working on their PhD. And so that guy, he was working on that for his PhD. But yeah, they do some really, really, really fascinating stuff. One of the things, that Jove project, back when I was in Caledon, I wanted to set up that antenna because I had.
Oh, did you?
Yeah, I had the space that Eric and I talked about. That I was going to get the kit because they have the kit there at Dayton, right? You could go and get the kit, or you could order it. And I was thinking about going and setting it up, and I thought, well, the chances of me setting that up and getting the antenna up are probably slim to none, right? Yeah, but it's fascinating stuff, Kevin. Very good.
The Jove thing reminded me, I forget the guy's name now, but he was the VE7 who had that popcorn blog spot that he changed onto, it has a very home builders blog. Anyway, he got into this radio telescope stuff and listening to the signals that were coming from Jupiter. I'll see if I can find it, and I'll post it.
Dave, you weren't talking about Nathaniel Frissell, were you? W2NAF. He's sort of I think the lead guy in a lot of the Hamsai stuff.
May have been him, because at the time, I don't think he had gotten his PhD. I think he just got his PhD recently. Like, I think within the past 3 years. or so. I was just Googling him, and I see it's Dr. Nathaniel.
Oh, it's
Right.
Dr. Oh, okay.
Yeah, I think he's got his PhD now, and I think back then he was still working on his PhD because I remember at one Hamsai forum they brought him up and they were applauding him because he had finally gotten his PhD or something.
Yeah, I think that might. Yeah, when I saw him at Dayton, yeah, that was a couple of years ago now, right? So.
Yeah, and at Dayton they have got some really fascinating talks.
Yeah.
Really
they do.
interesting stuff.
Hassan has a question.
Yeah, this is really interesting because actually all of these things are things I wanted to get into before I was into ham radio, and it's nice. I actually know a little bit enough about antennas and radio to actually participate now. But I got a book a while ago from the U of T book sale about. It was written in someone's PhD thesis from the 60s, and he gave circuits on how to build your own radio telescopes. They're all just simple MOSFET amplifiers. But one of the things he said is if you want to observe Jupiter, take an FM radio and tune it past the end of the dial to 110 megahertz, and then just take the output, record it on a tape or something, or look at the volume meter and plot it over a day, and you'll see variations or something. And it could be that simple. All they're doing is plotting signal strength. That's like receive.
Yeah, that's really all they do. And just in case anybody's wondering, I put a bunch of links in the chat. So if you want to pull the links down and go look at stuff, they're in the chat.
Yeah, I really want to get involved in some of this stuff again now. It's going to be.
I think this will be a big rabbit hole, but that's okay.
I just really grazed the surface. Like there's really a lot more there. So,
well, it's interesting. Hassan says he was going to go down that path first, and then he found the rabbit hole of ham radio, and that's got a pretty big hole there too.
Yes.
Have you seen, Kevin? Did you see that satellite that got launched? I don't know if it was a year or two ago by that guy. He put up it's a small little CubeSat. And do you know what LoRa is? You know what LoRa is,
yeah,
right? Yeah, that's all it does. It's just LoRa, and it does a pass. And people are building their little LoRa repeaters to send a signal and hear it coming back. And they're timing it when that satellite goes over. If you go on YouTube, you'll see a whole bunch of people building these LoRa base stations now.
I have a LoRa transmitter and receiver somewhere in a bag, in a box, in the closet.
Yeah, because if you actually look at one of the posts you made, it talks about that guy. What's the guy's name? Julian Fernandez. That's the guy. He's a young guy, and who put this together. And there's an interesting story. I can't remember the story, but there is an interesting story about how his satellite got launched.
Yeah, no, it's a very deep rabbit hole. There's so many things you can go check out.
You better hurry up and retire so you can do it justice there, buddy. Phil, you had
I'd love to. I'm jealous of all you guys.
Phil, you had a comment or a question?
Yeah, Kevin, those links that you include there, do they include the ones on your last slide?
No, but I can put them on there too. Yes, that's a good point.
Yeah, please. They look pretty interesting. And for Dave, you mentioned the group's IO. What's the name of that group?
Actually, search. I posted that probably 2-3 years ago. If you just go and search on the group's IO group, you'll see a post about it.
Yeah, I'm actually on it too, Dave. And I don't remember it either. I don't.
Yeah, just search the groups that IO and search for Hamsai.
Yeah, that'll pick it up.
Okay, thank you.
Any other comments or questions? Which part of this hole do you want to find yourself into, Kevin? Like, what are you looking at more?
I like the Hamsai one. I think it'd be cool to have a magnetometer and GPS and all that kind of stuff out back, just logging data. Just who knows, right? And maybe you can take a look at it and go, oh, my signal just faded on 20 meters, and oh, something just happened, right? Like don't know what it might be, but maybe there's some correlation there, right?
Yeah. Okay. Drew, you have a comment, question?
Well, yeah, I was just wondering about a magnetometer with that level of sensitivity. What limits are they going to put on the power of the ham radio operator? Are you going to influence one with the other?
No, I don't think so. They actually bury it a couple of feet below the ground as well.
So we're not really strong enough. I just wondered if you were mentioning.
And I think it's fairly long, like it's averaged over a relatively long time. So short-term stuff like that, I don't think affects it too much.
Yeah.
What actually is it picking up? Is it measuring?
The strength of the Earth's magnetic field.
Okay.
But to a precision of 10 nanoteslas. That's their goal, which is really, really low.
Okay.
Or sensitive, I should say.
Hassan has another comment.
Yeah, I read about this guy named Renato Romero who built one of these magnetometers and buried it in his backyard. He used a few kilometers of fine gauge wire. I'm not joking. And he wrapped it around a PVC pipe, and it was like less than a few hertz. But then, it's really sensitive. And if a truck passes by on the road, he'll pick it up. But there is another citizen science project. I know it's just ridiculous. Like it's several Henrys or something. There is another project. We can build a soda pop can magnetometer. You just take a magnet, you epoxy it to a mirror and hang it by a piece of fishing wire, like a fishing line. And then you hang it in a pop bottle, and then you shine a laser from one end onto it. And as it swings, it'll cast a reflection on the wall. And apparently that's really sensitive too, enough to detect the Earth's magnetic field. And
I was going to say, does it do earthquakes as well?
That comes for free.
Drew, did you have another comment? I thought I saw your name last slide. No? Okay.
No, sorry. I was learning how to lower my hand.
Oh, okay. Dave, you had another comment?
Yeah, Kevin, there was a project I came across years and years and years ago. It was when I was investigating grounding.
Grounds, yes,
that conversation. But I ran across this article, and I can't remember. I'd have been trying to find the article, and it was a ham radio publication. And what it was this guy, he was experimenting with passing radio waves in the Earth's surface, where he'd send very low frequency RF through the Earth's surface, and he would put probes into the ground, and he was able to communicate over a long distance with this low frequency waves in the Earth's surface. And I've always wanted to find that article and look at it and do something like that, because it was really, really fascinating how he goes about sending the information and the physics behind it. It was really, really interesting. By you talking about, burying these magnometers, I just, that came into mind. I just remembered that. If anyone knows of the article, post it, let me know, because I've been trying to find it and I can't find it.
You should look into telluric currents and ley lines.
What?
Ley lines. It's an ancient Celtic myth that there were these pathways through the Earth where you could communicate through, or something like that.
Okay.
No, this is real. This is actual ham radios who've done experiments and gotten it to work, and were able to pass signals.
Well, we could go to Ireland and go into the pub over in Ireland and see if we can find what Hassan is talking about, the Celtic influence there, right?
Yeah, I think we'll find something else.
Yeah, no kidding. Okay, any other comments, questions? When do you expect to get started, Kevin?
Well, I was actually going to wait till the Hamsai guys get their stuff kind of done and tested and software written and all that, and then see what happens. And then that's another presentation.
Yeah.
Right?
That's right. Okay, that's good. Great, thank you. Okay. Okay, I guess it's on to me then. Can we see that?
Yep.
Okay, another one of my series. I've done it for 3 of them now. Velty Spice and the real world comparisons. And this time I picked the instrument amplifier. And what is it? Well, it's used to provide a large amount of gain for very low level signals, and usually in where there's a lot of high noise levels. The main properties of an instrument amplifier is high gain and large common mode rejection ratio, CMRR. And that is, CMRR indicates the ability of a differential amplifier to suppress signals common to the 2 inputs. So therefore, any signal that you're interested in should only appear on one input or with an opposite polarity on both, and very high input impedance. Comparing to a regular op amp, what are the differences? Well, not all amplifiers used in instrumentation applications are instrument amplifiers. It's the configuration of the op amp circuit that will determine if you're going to classify the circuit as an instrument amplifier. So you can use a regular op amp, which is actually what I've done here. The instrument amplifier is a closed loop gain block that has a differential input and is a single-ended output. And in the case here, it's not unlike an op amp, which is closed loop, is determined by external resistors, whereas the instrument amplifier has an internal feedback resistor network. And the instrument amplifier basically is a device that amplifies the difference between the 2 input signal voltages, and then while rejecting signals that are common to the both inputs. Okay, so for my setup here really was just a couple of power supplies, a couple of meters, pretty simple. On the right there is the board that I built. The board design was done by Dave, VE3EAC, and he also did the milling of this board as well. He thought I was getting bored and had nothing to do, so he milled an extra board and then came over and dropped it off and said, "Here you go, have some fun with it." I thought, "Oh, great." Anyway, it sat in the shelf for a few weeks, and then I got really curious and thought, let's go down this rabbit hole, small one, I thought, and let's see what this is all about. So here's the circuit that I used. Now I got a question here, why the use of the LM358? Dave, I forget what the project is that Dave was building or working on, and he needed an instrument amplifier circuit for it. And he does have some instrument amplifier chips, but they're about $10 a piece. And he thought, well, you know what, let's just use a regular cheap LM358 and see if that will do the job. And then if somebody else needs one, then you can go that route without having to spend $10 on a chip. Where I think a DigiKey, you can get a 358 for, well, it's under $1 anyways. The circuit here, I guess, down the lower left side here, this was for the zero adjust, and I measured values and all those kinds of things, and just to see what they would turn out to be. And in both the case of Spice and in the real world, I found that basically you can tell by the value here is pretty much nothing. And over here, that's the span resistor. We'll talk about that a little bit going forward. And then here's your variable voltage in, and that's pretty much it for this one. Yeah, nothing much else fancy about that circuit. Okay, so the results I got. The red line is V in. Oh, the scale on the bottom. For some reason, I couldn't get the decimal point to shift over to the left. So after quite a while trying to figure it out, and I couldn't, I just left it at this. So when you see a 1, a 2, and a 3, it's actually 0.1, 0.2, 0.3, etc. So because I thought it might make a bit of a difference, I actually measured the resistors that I was using. In the case here, you can see where span says 986 ohms. Well, that's a 1K resistor, and the other one was 220. But I used the actual measured values, and same thing within the SPICE simulations. And then I did one where the span was shorted out. Now, in all cases, 3 cases here, you can the LT SPICE simulation was just slightly higher than the the real world measurements. The other thing I think was interesting is that where the lines in all cases start to knee over, the slope changes. Both SPICE and the real world were doing it at the same points. Here it's basically the same thing, but I'm just looking at the one, the higher one, the with the span resistor shorted out. And just so you can see it just a little bit clearer. And again, you can kind of see where each one, you know, they bend over at the same time or at the same location. So the next thing I did was I adjusted the zero, adjust up to 300 millivolts. And again, what did SPICE say it was going to do and what did the real world do? And they pretty much said the same thing. A little bit of a kink here. One of the things I did was on setting up my power supply, I was being anal about the voltage that was out. So because I had the third digit on the power supply, I just tried to adjust it for 0.1 or 0.1 point. After a while, after I got into it, I thought, well, I might as well keep going. I'll never do that again. It was just took too much time, and it was finicky as hell. And sometimes the measurements might not have pulled off the right spot, so that might explain what's going on here. But either way, it looks pretty good, I think. And here I increased it up to 600 millivolts. And I guess what's interesting about this particular profile of this line is that an extra slope came into play here. There's like 4 of them in here, whereas the other ones had 3. But again, both SPICE and the real world agree. Here I'm just comparing the 3 of them together, and you can see where this is just the real world measurements of the 3 different settings of the zero adjust at 0 volts basically, or very low voltage, and then 300 and then 600 millivolts. And here I just threw in the LT SPICE simulations as well. So they're all pretty close. This one here, I changed the power supply was set at 5 volts, supplying the op amps. And here I just bumped it up to 6 volts to see what the difference was. And of course the higher setting ones, it went up a little bit higher than the other one, which is understandable. So it basically went as predicted. But again, both SPICE and the real world picked up on that. Okay, this is where I thought things were going pretty good with this project until now. And I ended up spending far, far too much time on this part of it. But once I started it, I had to try to figure out what was, going down to the end. In the end, it was something that was very simple. Now, the red circle, I can't remember now why I put that in there. I guess if I did this presentation 2 months ago, I probably would remember. But anyway, somewhere along the way, I decided to do the math this way. And basically, gain equals 1 plus RF divided by RS. Now, RF is R5, this one right here. And RS is the combination of this resistor and this resistor added together in parallel with this one, and then add this one into the equation. Anyway, that all comes out to 1.84 for your gain. So SPICE says, okay, the top plot is V out, and V in is the middle plot, And then the bottom plot is where I just basically took V out divided by V in. Now, at first glance, you would say, okay, the gain is all over the place. Well, it's not. If you take a look at the scale, and you can see the very first line here is just a tad over 1.84, and then the next one is at 1.842, and the maximum one here is at 1.856. So the difference really is about 0.01, 0.02. So for the gain, so I think that's pretty good. So I thought all was going really well. But there's a big but, and this is where I finally blew up on doing math. And that is the real world measurements. I probably shouldn't even say this because it goes south here. The real world measurements, if I just take V out over V in, the results are about double the gain. It's about 3.2 is the gain. So I'm not too sure why the discrepancy there when all the other measurements and spice were all agreeing until it came to this little final thing. Anyway, I never had a chance to really dwell into why or what, but I'd had enough of the math situation by this time. Anyway, that's all I've got there. Any questions? Where are we? Okay, we're back here. Oh, I'm not stopped sharing. Hassan, yeah, you got a question?
Yeah. If you're using an LM358, it's really a different differential amplifier now, not a instrumentation amp, right?
It's the configuration. It's not. It's not the amplifier. It's how you wire it up that would make it you could classify the circuit as an instrumentation amplifier.
Yeah, I think the only difference is an instrumentation amp would have 3 op amps. 2 of them would be used to buffer the plus and minus inputs, and then the rest would be the same as what you had. And so I've always tried to figure out what the difference is. I mean, I think that's what I think it is. The instrumentation amp just has a really high input impedance because it's buffered on the inputs. Yes. Otherwise, your input impedance is determined by your resistors, but for the iamp, it's kind of infinite.
Yes, that's correct.
Okay, and I guess the other thing is there's usually some resistor in the middle to set the common mode gain. I can't remember if you had that.
I'd have to go back. Where are we here?
Okay, this is some. I can't understand the networks on the plus side. Zero adjust, that's for the offset removal, I guess.
That was so that if you had no input, so 0 volts going in here, adjust this so that the output was 0.
That's for the op amps grounded. There's no negative swing. So the op amp is going to swing across that 0 adjust. You're moving the 0 adjust. Normally, if you've got a negative power supply and a positive power supply, it swings around voltage 0, the middle between the plus and minus rail. But since you've got it grounded, it has to swing between 2.5 volts. So you're supplying that 0 adjust as you're raising the 0 and allowing the signal to oscillate around a new 0.
It's only the problem is it's on the positive pin. So I'm wondering if this is not, that's why he had that roll off at the top. See, 0 adjusts.
It is on the positive pin.
Yeah, so is it adjusting the 0 or is it adjusting the top end?
No, it's adjusting the 0. That's why it says 0 adjust. That's
well,
adjusting.
That, but
here's the result.
Zero.
Where are we here? I mean, there you can see the effect of making that adjustment on that pot. If you were supplying 300 millivolts, well, there it is with the 0 adjust at 0. that straight line up until it bends over like this here. Bump it up to 300 millivolts, the zero adjust, and this is what the response curve is. And if you bump it up to 600
Well,
millivolts,
wait a second. Where's the input going into this amp?
the variable voltage, you mean?
The input. Oh no, so the input's going to the
Input's here.
other op amp. Okay,
Yeah.
no, ignore what I'm saying. If the input was going into that first LM358,
No.
so that LM358 there is supplying some kind of an offset
Yes.
to that to go into that minus pin.
But if you measure it and watch this, you can have, and with no input here, you adjust this to get zero out.
Okay, so yeah, the left-hand side is just buffering the resistor network.
Now, this is
Somehow.
what was originally envisioned and designed. I found in practice, though, it was virtually, this was to get zero out with zero in, you're basically zero here, which kind of makes sense. Now, before I forget, I did upload to the Homebrew section of the club website a bunch of documentation where where Dave originally got this circuit from. There's I think about four uploads there. A couple of them are the data sheets, and this circuit came out of, I think, on one of the pages of one of the data sheets, and also there's a good write-up there's a designer's guide to the instrument amplifier, and so there's a lot of information in there about it.
Hey Hassan, I always thought an instrumentation amp is what's it called, where you've got the both? You've got a plus or minus?
Differential.
Differential. Isn't that an instrumentation amp supposed to be a difference amplifier? So you can get like a common mode?
Right,
Yeah.
and a normal a regular differential amplifier has two resistors on the inputs, but an instrumentation amp has buffered op amps, and so you have infinite input impedance. A differential amplifier is like 100K ohms input impedance kind of thing. So yeah, I can't actually recognize what this amplifier is.
Yeah, that's what
The
I'm saying.
write-ups that I uploaded will probably explain it better than I have. My goal here really was like this. The genesis of this whole thing was to not use an actual instrument amplifier chip. It was to just see if you could do the circuit with an ordinary op amp that would do the job. And this circuit actually comes out of one of those documents that I upload. I think it's a direct lift out of one of the data sheets, but there's a similar circuit on this as well in the designer's guide book.
Okay.
But the thing that I take away from it, whether the nitty gritty details is interesting of the instrument amplifier, but in one respect with this one is the comparisons of LT Spice with the real world, and how did they compare? Were they close? Were they way off? And in this particular case, the only thing I found that was off was that the gain of taking the data, the gain of the in and the out, and then just doing that math, you come up with about 3.2, whereas Spice and the method of using the resistors as the calculation for what would your gain be agreed at 1.84. So
That is impressive.
But you can't. I got a couple of comments. One is that you can't apply just a regular formula to this. You have to go back to first principles and trace the current through the network and see how the current is going and formulate the voltage out as a function of the current. Yeah, you have to go back and look at it. But Kevin, you can't do this. That I don't think that applies. But Kevin, don't you use instrumentation amps? That's your job?
No, not so much. I mean, I certainly don't design them, but I mean, some of the stuff I use, is differential amplifiers on the analog, sensor inputs and stuff. But I don't really use a lot of instrumentation ones. But yeah, to your point about what you're saying, you have to analyze the network. I agree, because like the junction of R2, R3, and R1, is going to be exactly it's going to be at the zero adjust voltage, right? Because it's a non-inverting amplifier. It's a non-inverting amplifier. So it's going to be at the same voltage. So your feedback resistance, I don't think is necessarily going to be R2 in there. It's certainly going to be, R1, and then maybe R1 and R4 in parallel. And then because the output of even the voltage around R3 is going to be, the offset. Well, actually, it's going to be the output voltage of U1 is going to be the same as the offset voltage, because it's going to be twice, because it's a gain of 2, right? R3 over R2, R3 plus R2 over R2. So if I remember right, so it's a gain of 2. So you have a signal there, and I agree with what you're saying. You have to go back to first principles.
Yeah, you have to go back, and that's what Peter, and that's what I was showing you with the Dave Jones video, because he shows you how to calculate the gain from first principles. And that's what you have to do with this amp. You got to go back to first principles, and you got to do the loop, what's it called, the Kirchhoff loop or
KVL.
So
yeah, there's one more thing, that these resistors are very high value, 47K. So the input impedance and stuff of this amp is only like a few hundred K, I'm guessing. So you're going to get like a few percent error, because you have to take that into account as well.
right. You mean to help explain why the gain came out different?
Yeah. Actually, on that point, did you use the nominal values in the formula? Or did you use measured values?
Measured.
Okay.
I use measured values in here. Yeah, for here.
Uh-huh.
And
for your spice?
yeah, I didn't use the nominal. Well, I think the 47K actually worked out to measured 47K. The 10K measured 9,000 and change.
What you could do also, Peter, is that you could, like, as what Kevin was saying, the part that's kind of disruptive here is the voltage U1 is supplying. So if in the LT Spice, you could take a look at the voltage there at U1, and then from first principles work backwards, right? And plug that voltage in, because it's a known voltage, and then you could kind of fudge the gain. But then you're getting to see how to calculate the gain, right?
But what throws me for a little loop here, though, Dave, is this calculation is based on these resistors and the measured value, and it came up to 1.84. When I took the data from LT Spice of in versus out, it came up with 1.84 basically.
Yeah, but you don't even have.
See right here, 1.85 is the back.
Go back to the schematic.
Yeah.
So you're saying the RF is the feedback, and RS is what's going to ground.
RS is these guys right here. RS is a combination of R3 plus R4 in parallel with R1, and then add R2.
But then you see your RF, your feedback includes those resistors too. Oh no, it doesn't, because it's going DC and it's going right to the minus input of the U2, right?
U2, yes.
Yeah,
Yeah, no, I'm not including R5 in this mess here.
So R5 is what's the this is what type of amp is this again? U2? Is that a
this is just one these both are in one package.
No. It's what's the shit. There's two different names for the two different type of op amps. Inverting, non-inverting. Is this an inverting or a non-inverting configuration?
This is
and what's the gain?
Non-inverting, right?
Non-inverting.
So for a non-inverting, is that the gain? So RS is that the resistor that goes to ground?
RS eventually, here.
No, in a I'm trying to see how that. Let me just pull it up. So that's a non-inverting amp.
Yes.
Yeah.
So it's a voltage divider. right? A non-inverting amp.
Yeah, there's a voltage divider, and so a fraction of the input appears at the minus pin. Yeah.
Right, and so the other resistor, the RS resistor, is what's supposed to be taking it to ground. That's the other half of the voltage divider. That's where it was going.
Yeah. I'm guessing that the U1 is saturating at some point, and that's why you had that roll off at the top. If you drove U1 with 10 volts, you might get a clean signal all the way through.
Oh,
Yeah, the problem is just the output from U1. Like if you assume that's a voltage there, then you could work out the gain, right? Because it's not just a combination of R1 in parallel with R3 and R4, because the junction of R3 and R4 is not the same. It's at a higher potential. So you have to kind of turn this upside down and look at the voltage from there. Look at the voltage across R4, right? And then everything else is a Thevenin equivalent, right? Something like that. You take R3, R1, and R2, and you get a Thevenin equivalent for that. And then you look at the gain with R4 and R5. You have to do something like that, right?
Okay. You see why my head blew up?
Yeah, no, but this is the stuff I love doing. This stuff interests the crap out of me, you know?
Yeah. In the end, for me, the math didn't quite work out the way I thought it might have, considering. I would say, though, that it did, no matter what the circuit is doing, Spice basically follows it fairly well. So that's a good thing, right? I guess it's just another way of validating LT Spice, I suppose.
Or it's a fluke. Why don't you change the values and see what happens?
And the only value I changed was the voltage supplying here. I changed those to 6. That was the only thing I changed.
Yeah, I would change the resistors and just see what happens. See if it still applies, right?
Yeah. Well, these resistors values came out of it was either the data sheet or the designer's guide to instrument amplifiers. I can't remember which one. So
because you got 47K resistors all over the place, it just may be a fluke that it comes out to be 1.884. I don't know.
Yeah. Anyway.
Yeah. I mean, if you tried to run this at a few megahertz, at that point, Spice would fail horribly.
Well,
like if you
but don't forget to go with a DC with a instrument amplifier. You're looking at DC voltages, really. You know, you're reading sensors, right?
Yeah, instrumentation amplifiers are very low speed.
Yeah.
But that's how we learn. Stuff like that. You don't understand it, and that's why I love LT Spice, because I go in there and I experiment and I play with things and I try and figure out why it works or why it doesn't work, right?
You should read Bob Pease's book about analog circuits. He has a whole chapter on why he hates Spice. And he's designed a few op amps, I think, and he tells it's actually quite fascinating. He's very much opposed to the use of Spice for modeling stuff.
I mean, I like that guy. I like reading his stuff, but I have no idea why he's so against Spice. I remember reading that article a long time ago, but I can't remember it now. But
I think his basic idea is that if Spice only works sometimes, but in other times it fails, but then there's no warning that it's going to fail, so you can't trust it.
Hasn't steered me wrong yet. Of course, I'm not. What I'm doing with it is nowhere near taxing the power of it anyway.
Well, I've discovered that some people, when they design things, they attract problems. Bob Pease is one of those guys. So his circuit designs, he just, like, some people just, they go through life and everything's a problem. They go to the store and the clerk treats them wrong, and other people just seem to breeze through, and yeah.
Who is that, Hassan?
a Bob Peace, Bob, a Pease.
Okay.
He has a book called Troubleshooting Analog Circuits, which is really fun. He's deceased now, but he worked with Bob Widlar and some of the people who designed some of the first popular op amps, and he's got some deep analog knowledge.
Okay, thanks. See if I
Yeah,
can find it.
he had a series of columns for National Semiconductor, which are really good reads.
Yeah. Did you ever see a picture of his office?
Yeah. His beard is messier than his circuits.
Yeah, there's no way you can clean up that shack. Very good. Okay, so anybody else have any more comments, questions? All right. Okay, like I said, there's some documents on the club website in the homebrew section if you want to dig into a little bit deeper, or at least see where this stuff had come from originally. Anybody else have anything that they would like to talk about? Wow, silence. Guess we can all have a drink pretty soon. Okay, well, that's all I have for tonight. I guess next up is, I don't have a schedule over there. So next up, I guess would be our mixer. I'm not sure the exact date in January. I don't have the calendar with me, and that will be Eric, right, Eric? Yeah, you see, yeah, you ask somebody a question, you can find out if they're actually there or not.
Yeah, it is. I am here just momentarily though, but January the 5th, Wednesday. Yep, that's me.
Okay, good stuff.
Next year.
Next year.
Next year. Oh, yeah, we can do a show and tell what everybody got from the tree, right?
Yeah.
Okay, well, I guess with that, I guess we'll say 7-3, everybody. Thank you very much for attending, and we'll catch up with you in the new year. Well, I'm sure we'll talk before then anyway.
Merry Christmas, all.
Night all, yeah. Merry Christmas. Good holiday.
Take care.
Good holiday, yeah.
Yeah, right.
Yeah, Merry
Peter,
Christmas.
I'm working on SimSmith on Sim charts, Smith charts. I'm getting there.
Stefan, you want to stick around?
Oh, you're getting there, right? Okay.
Sure.
Michael.
I'm getting there, but I'm not committing till when I do a presentation. I'm too
Okay.
scared to commit.
Well, while we talk about commitments or something like that, did you want January, February, Dave? Yes. Dave?
Oh, you talking to me?
Yeah.
Oh, okay. I'm sorry. I'm tuned out.
No kidding.
Drift.
Not Kingston, Dave.
Yeah.
Did you want the January, February spots?
Like a February. I'll do a presentation. Because I've been playing around with MOSFETs,
Yeah.
and I've gone down the MOSFET